In large-scale industrial machine learning systems, the quality of your model isn't just about the algorithm, it's about the data you feed it. And at the heart of that data lies a critical, often overlooked step: feature selection. Features are the building blocks of prediction. They capture everything from user behavior to content metadata, and in modern recommendation systems, you might be working with hundreds or even thousands of them. But not all features are created equal, and choosing the right subset is a challenge that directly impacts accuracy, efficiency, and long-term maintainability. Traditional feature selection methods rely heavily on labeled data and statistical heuristics, correlations, mutual information, variance thresholds. These work well in data-rich environments. But in real-world production systems, labeled data is scarce. Models evolve constantly, and there are hard constraints: team ownership, pipeline dependencies, fairness requirements, even system latency. That's where things break down. Enter Model Feature Agent, or MoFA, a new framework from Meta AI that reimagines feature selection not as a statistical optimization problem, but as a reasoning task, one that leverages the power of large language models to think, weigh trade-offs, and make decisions with context. So how does it work? At its core, MoFA treats feature selection as a sequential reasoning process. Instead of blindly ranking features by correlation or coefficient size, MoFA's LLM agent evaluates each candidate feature not just by its numbers, but by its meaning, its context, and its impact on business goals. Let's break it down. Each feature is represented as a structured tuple: a name, a natural language description, and rich metadata, like its importance score, correlation with key metrics, and even group affiliations, AG, which engineering team owns it. This information is fed into a prompt, where the LLM reasons step by step. Why is this feature valuable? Does it conflict with others? Is it redundant? Could it introduce operational overhead? The output isn't just a list of selected features, it's a traceable, interpretable decision path. For example, selected feature, P external share times P profile tap. Reason: this interaction captures users who both share content externally and engage deeply with profiles, indicating high social intent. It's highly correlated with session duration and has low redundancy with existing signals. Prioritizing this over isolated click metrics improves engagement lift while avoiding overfitting. This level of explainability is transformative. It turns feature selection from a black box into a collaborative, auditable process, where engineers and data scientists can understand why certain features were chosen. But here's the real challenge: industrial systems have thousands of features. You can't fit all of them into a single LLM prompt. That's why MoFA introduces a divide-and-conquer strategy. Phase 1, the feature space is partitioned into disjoint buckets, say 5 or 10, each small enough to fit within the LLM's context window. The agent performs parallel, sequential selection within each bucket, picking a slightly larger number of candidates than needed, e.g., 5 times the target size to preserve high-value signals. Phase 2, all these local candidates are merged into a refined pool. The LLM then performs a final global reasoning pass, selecting the top K features while evaluating cross-bucket dependencies, like redundancy, synergy, or group clustering. This two-phase approach ensures scalability without sacrificing depth. It's efficient, consistent, and most importantly, robust. Now let's see it in action. In one real-world case, we used MoFA to predict true interest and timeworthiness, whether content truly reflects a user's interest and whether it was worth their time. We had 1,030 features across 187 operational groups. The goal: improve accuracy while reducing cross-team dependencies. Traditional lasso regression picked features based purely on statistical correlation, leading to selections scattered across 187 groups. MoFA, by contrast, focused on fewer, higher-impact groups. At a feature budget of 500, it reduced group count by 54%, from 187 to just 85, while matching or exceeding lasso's accuracy. Why does that matter? Because each feature group means a different data pipeline, a different team, a different maintenance burden. Fewer groups mean faster iteration, fewer conflicts, and a more sustainable system. In another case, we tackled value model enhancement, a core signal in recommendation systems. The existing model used a simple linear combination of engagement signals like likes and clicks. But we suspected that interactions between signals, like a user both sharing and tapping their profile, could reveal deeper engagement. So we asked MoFA to identify promising higher-order interaction terms. From a pool of 400 candidate pairs, it selected the top 10, 3 of which were tested in live experiments. The results: a 0.055% increase in daily app sessions, statistically significant. That might sound small, but in a system with millions of users, that's tens of thousands of extra sessions per day. And all from a single, intelligently selected interaction term. Finally, in notification behavior prediction, we had a multitask model with 38 prediction targets and over 7,500 features. Manual selection was impossible. MoFA selected 4,000 features from 8,169, using its divide-and-conquer strategy across 10 buckets. The result: a 0.198% improvement in normalized entropy loss for predicting user dismissals, while using fewer features. Compared to random sampling, MoFA delivered a 0.332% win, proving it's not just smarter but more efficient. So what makes MoFA different? It's not just that it uses LLMs. It's that it uses them right. It doesn't just rank features. It reasons about them. It considers semantics, metadata, constraints, and trade-offs. It asks, does this feature align with our goal? Is it redundant? Who owns it? What's the cost of maintaining it? It turns feature selection from a reactive, data-driven task into a proactive, strategic one. Of course, it's not without limitations. The sequential nature means selection time scales linearly with the number of features, though this is usually acceptable since feature selection is an offline step. And while the LLM can reason across thousands of features, input length still limits scale. Finally, because it's greedy, selecting one feature at a time, it might miss optimal combinations that only emerge when selected together. But these are challenges for the future. The core idea, that reasoning can be the engine of feature selection, is already proven. MoFA isn't just a tool. It's a new paradigm, a bridge between interpretability, flexibility, and scalability. It shows that in production AI, the most powerful models aren't always the most complex. They're the ones that think the right way. So if you're building or maintaining large-scale machine learning systems, whether in recommendations, notifications, or beyond, consider this. The next time you're overwhelmed by feature space, don't just crunch numbers.